start looking at this idea of vectors, which becomes very useful for solving particular problems in geometry, problems in motion, coordinate geometry. So we certainly use vectors more than you would have used in physics, because physics is just one application of it. All right, so last topic we were talking about the translation of graphs. So the parabola y equals x squared, we translated it 2 units to the right, 1 unit up. What's the new equation of the parabola? So here is our parabola, shift it 2 and then up 1. So there's the new position, and we could transform it, and we end up with x minus 2 all squared plus 1. So what on earth has this got to do with vectors? We found it by using our translations. I mean, that's how we actually found it. But that translation we can combine into what we call a displacement vector. So every point, and I'm using the orange in there, has been moved to a new point. So if I just draw a ray, starting at where the original point was, going to where the new point is, okay? That ray, if you like, is called a vector. And this is how we do it. But I can do that to every single point and say, well, where's it been translated to? And the thing we notice is all those vectors are exactly the same in length and direction. Okay? So they are indeed the same vector. And so we could write it like this. Now I'm using capital X and capital Y so I don't confuse it with the original coordinates. So the new coordinates are like capital X, capital Y. And so what did we do? So the top row is saying what happened to the X value. To the X value I added 2, and to the Y value I added 1. So that 2, 1 is actually the vector. Every single point, every single point has had 2, 1 added to it. This then ties in with what we looked at with parametrics. I could then work out the new equation by saying, well, hang on, let's go back a bit. X and Y, the original parametrics of the parabola. Now there's lots of different ones I could come up with, and probably the simplest one for y equals x squared is I'd say, well, x is t and y is t squared. And that would come up with the equation y equals x squared. So now all I do is read across and I say, well, that means my new coordinates, or new equation I should say, so it means our new equation, the x parameter is t plus 2, the y is t squared plus 1. And just like we saw parametrics, eliminate the parameter. So x is t plus 2, rearrange that, t is x minus 2, sub into the y, and bingo, there's the equation that we came up with before with the translation. So we get x minus 2 all squared plus 1. Okay. So there's one application of a vector. So some definitions. Okay, so PQ, and you'll notice when we're talking about a vector, we put an arrow on top. So that's to indicate we're not talking about an interval, we're talking about a vector. And that would be the displacement vector, and the order of the letters becomes important. And so that's why we draw the arrow to the right. So the left-hand side, the first letter we write down is the starting point of the vector, often called the tail. And then the second letter is the end point of the vector, often called the head of the vector. So this would be the vector PQ. Some other notations? We often use lowercase letters to represent vectors, but with a tilde underneath. What? A tilde, that's what that's called. So, P with that. And you'll also sometimes see in textbooks the lowercase letter, but bolded. Now, I steer away from that notation, basically because when you're handwriting, it's very hard to write something and say, oh, this is in bold. So, unless you go over it and over it and over it and over. So that's why it's easier to use the tilde rather than making it bold. Now, the beautiful thing about the vectors is what we just saw is they can move and you still have the same magnitude. But we can uniquely identify it by looking at any one of the vectors. Okay? Because the size of the vector, which we call the magnitude, the size, and the symbol we use, it's familiar with us, the absolute value sign. Because that's exactly what absolute value meant. We weren't concerned whether it was -4 or +4. If we're talking about absolute value, we just wanted 4, the size of it. So it's exactly the same notation. So that represents the magnitude of the vector. Now, negative vectors simply go in the opposite direction. So the one we had before, so if PQ represented the vector P, then QP would be -P. Same vector but going in the different direction. The head has become the tail and the tail has become the head. Now parallel vectors, same as parallel lines, parallel intervals, still coordinate geometry, they have the same slope. So the vector PQ would be parallel to the vector QP. Then there's this weird vector, the 0 vector. And it's just a point, because it's going from P to P. So it has no magnitude, but it also has no direction. Because if you're starting at P, finishing at P, how do you know which direction you went off into? You haven't gone anywhere. So 0, just like in our real numbers, where 0 is this really strange number that we use, but it has all these things we can't do, like you can't divide by 0, and 0 to the power of 0, all those sorts of things are sort of meaningless. It's the same with vectors. So the 0 vector, what we say though, is it's parallel to every vector. Because we haven't decided which direction we're going in, you could theoretically say it's parallel to, well, even though it doesn't have, see, another weird thing about 0. Even though it doesn't have a direction, it's parallel to everything. A scalar, well, that's when we're not concerned about the direction. So it's just a real number. So the magnitude of the vector will be a scalar, just the number. How long is it? So I could represent like this. Lambda, where lambda is a scalar, would be a vector. It's in the direction of P, but the length of that vector would be the length of P times whatever lambda is. We've just multiplied it. Now, a position vector is a very special displacement vector. And that's where we join it to the origin. So, sorry, well, join it or start it. Probably better to say start from the origin. Right? That's what we call a position vector. Okay, so adding and subtracting vectors. When you want to add them, you place vectors head to tail. So you basically join them together. So there's vector A, and if I want to add vector B, then that would equal A plus B. So I just slide it, because moving it, translating it, does not change the vector. So I just join it on. So the answer then would be, I join the head of the first one to the tail of the second one, and so that would be A plus B. And the beautiful thing is, it doesn't matter, because it preserves the addition. Remember we talked about commuting? Well, it's the same here with vectors. You can add in any order. Because if I'd gone, oh, there's B, plus there's A, so B, add on A, we get exactly the same vector. So another way of expressing that, I could say PQ, there's PQ, plus QR is PR. It's basically the tail of one, the head of the other. But look at the direction, that's important. Now, to subtract, we place them head to head rather than head to tail. Another way of thinking about that is you add a negative vector. So there's A. If I want to go minus B, then there's A, but minus B. The what, negative vector, same angle there, but it's going in the opposite direction. So we end up with A, negative B, and that would be A minus B. Notice, if I was to join all these things up, we end up with a parallelogram. And the adding and the subtracting of the two vectors become the diagonals of the two parallelograms. One diagonal is A plus B. The other diagonal is A minus B or B minus A, depending on which direction you're going. Remember, subtraction does not commute. Addition does. We actually get going in the opposite direction. Same length, but going in the opposite direction. Multiplication then. Well, first of all, by scalars. And that's what we were just talking about before. It simply enlarges it by whatever factor you're multiplying by. So whatever the size of the scalar. So if there's A, I could double the vector and we get 2A. I could go in the opposite direction and halve it. I get minus half A. But again, all of these are parallel because the scalar has not affected the slope. All right, let's do this problem then. So we can use vectors for geometry. So ABC is a triangle. We're saying, well, vector AB is A, AC is C, and it's lost its tilde. So I wonder what happened there. There should be tildes under those A's and C's, shouldn't there? P and Q are the midpoints of AB and AC respectively, and R is a point on the vector BC, so RC is twice BR. The tildes have come back. Express BC and PQ in terms of A and C. Well, BC, I could say, is AC minus AB. Head minus tail. So that's C minus A. PQ, okay, if I was to join up PQ, it's halfway. P was halfway. So it's going to be a half of AC and a half of AB. Which way round? We want head minus tail. So PQ, P's got to be the tail. So we get half AC minus a half of AB. So we get half of C minus A. Compare the vectors. So what they're getting at is, well, actually, if we were to draw in PQ, we'd find it's the same as a half of BC because it's the same vector but multiplied by the scalar of a half. So what geometric property does that demonstrate? So what have we done? We joined up the midpoints of those two sides. So the line joining the midpoints of the two sides is parallel to the third side. Because we said those two vectors would be parallel. But the scalar's telling me but half its length. And so that's the property of the triangle we've just proven there. All right, let's have a look at BR and RC. So BR would be 1/3 of BC. So we now know BC is C minus A. So we get 1/3 C minus A. RC, 2/3 of BC. So 2/3 of C minus A. And then finally it says, show that AR would end up being this wonderful expression. So AR, how could I get the vector AR? I could go AB plus BR. Now AB, we said was A. BR, we just found, 1/3 C minus A. Add them together, and we end up with, there it is, what we're looking for, 1/3 2A plus C. Alrighty, there's a little introduction to our vectors.